Good morning, calculus students. Sorry I couldn't be there with you today. So, since I'm not there with you, we're going to do this lesson through video. Today's lesson is continuing with using the chain rule that we started learning about on Monday. And we're going to be looking at more challenging chain rule problems, and then we're going to also be looking at the derivatives of the logarithmic functions and also the exponential functions. So we already know one of these derivatives. We already know that when we take the derivative of e to the x, the result of that is again just e to the x. So it turns out that when you want to take the derivative of an exponential function with a base other than e, so a is any number except for 0 or 1. Actually, I should say it's positive as well. It's a positive number, but it's not 0 or 1. Then the derivative of a to the power of x would also have itself in the derivative, just like e to the x did, but then I would need to multiply that by the natural log of a. And this, remember, is just a constant. So you'd have your function a to the power of x, and then it would be multiplied by this constant where you take the natural log of the base. Now, just for a moment, I just want to show you if a was the same as e, then let's just use the a to the x formula. The derivative would be a to the x, but I'm saying a is e, times ln, natural log of the base a, which if it's e, would be natural log of e. And recall that the natural log of e is 1, so the derivative of that would just be e to the x. And so you can see that really these are the same formula. We just like to remember that when it's e to the x, we're technically multiplying by 1, so e to the x is its own derivative. But with any exponential function, you would have the base to the power of x times ln of the base. The proof of how to get this derivative actually can't be done until after 2.5. So we're going to come back and revisit why this is the derivative once we have more tools at our disposal. For now, I just need you to start the process of memorizing it, add it to your long growing list of things to memorize. Okay, and then in addition to our derivatives for exponential functions, we now are also going to show you the derivatives of the log functions. So we typically start with a base e. So as a reminder, ln of x is the same thing as a log base e of x. The derivative of that function is equal to 1 divided by x. So whatever was on the inside, we divide by it. 1 divided by that number. And again, the proof of this is coming later after we have learned some more stuff in section 2.5. Then the derivative of a log with any base. So again, a is a positive number. By definition, we always use positive bases with logarithmic functions. But a is neither 0 nor 1, because then it wouldn't really be a logarithmic function. So the derivative of a log of any base is going to be very similar to the derivative with a log base e. It starts by dividing by whatever's inside the log, 1 over x. But then again, you multiply by the constant. This again is a constant multiple. And the constant that's multiplied here would be the natural log of whatever this base is. And again, the proof of this, again, is coming in after section 2.5. But for now, I just need you to start the process of memorizing these. So when you have an exponential function with a base e, it is its own derivative. When you have an exponential function with a base a, it's almost its own derivative. You just have to multiply it by this constant, which is the natural log times the base a. Then for ln of x, its derivative would be 1 over x, dividing by the value inside the log. And then for a log of any base, it starts off the same way, except that we're multiplying by that same constant multiple again in the denominator. So x in the denominator is getting multiplied by the natural log of a. So we're going to look at a couple examples here where we are going to combine these derivatives of log functions along with the chain rule that we had learned about on Monday. So as a quick reminder, the chain rule just says that when you are trying to take a derivative of a function that has another function plugged inside of it, So we call this a composite function. We start by taking the derivative of the outer layer, leaving the inside function completely intact. We don't change it at all. But then outside of that outer layer derivative, we multiply by the derivative of the inside function. So if you look at the way that this function is set up here in example 1, I have my outer layer of the natural log. So the natural log is on the outside. But then inside, I have this inner layer, which is a quadratic function, 2x squared minus 1. So this inner layer here has been plugged inside of the natural log. So when I'm taking the derivative of this kind of a function, I have to start by taking the derivative of the outer layer. So I'm going to start with the natural log derivative. So my answer for this would start by applying the derivative rule for natural log of x, which is 1 over whatever is inside. And in this case, what's inside is this entire expression of 2x squared minus 1. So that whole entire inside part of natural log is what ends up in the denominator when you're using the derivative rule. But because that inside part is more than just x, like it's a function of x, we can think of it as a g of x, then after applying the derivative of natural log, I need to multiply that by the derivative of my inside function, which in this case is 4x if I use the power rule. Maybe I'll think of that as 4x over 1 so I can simplify a little bit. So my final answer for this derivative would be 4x divided by 2x squared minus 1. This function here would indeed give me the slopes of this natural log function up here. Now in example 2, the outer layer is no longer the log function. So notice the way that this function is set up. The power of 3 is assigned to the log. So this means that I'm raising my log function to the third power. So this time my outer layer is raising something to the third power as opposed to the log. And my inside layer, which is this guy right here, would be my log function. And then just as a reminder, when you have a log function and there's no base written, then we understand it to be a base of 10. So in this case, a from my formula earlier is 10. Here's our formula earlier. A is whatever the base of your log is. So when you have a log without a given base, the default there, we understand that number is to be 10. Okay, but now back to the chain rule where I'm trying to take the derivative of this. So I have to begin with the outer layer, which is a power of 3. So for the outer derivative, I would apply the power rule. I would just take that 3, bring it in front, and subtract the power by 1. Meanwhile, keeping my inside function completely intact. But because the inside of this power of 3 was more than just x, it was a function of x, I then need to also multiply by its derivative. So the derivative of a log function of a base 10 would be 1 over the x, that was inside the log, times this constant of ln of 10. I have to multiply the x in the denominator of the derivative by the natural log of this base, which is just a number, but it's a number that I can't simplify any further without decimals. So I'm just going to leave it as ln of 10. Now this one, I might want to just sort of combine my constants together and maybe even this outer x. So I'm going to multiply this part together with this 3. We're going to think of it as 3 over x times ln of 10. And then all of that is being multiplied by the log of x squared. Or you can write that as log squared x, the way it was written up here, either way. And this would be our fully found derivative of this function. So this equation here would give me the slopes on the graph of this log cubed x function. Okay, so here in example 3, now I have an exponential function. And in that exponential function, I noticed that my base is 2. So that would be the a part of my formula for the derivative of an exponential function. I also noticed that inside the exponent is a function of x. I have like a g of x function because it's more than just x. It's 3x. So I'm also going to need the chain rule for this problem as well. So I'm going to start by taking my derivative of the outer layer. So maybe I should write out what that is. So the outer layer is 2 to a power. And then the inner layer is the function that was plugged into the exponent. So it's what went here. So it's a simple function, but it's still a function of x. It's 3 times x. So when I take the derivative using the chain rule, I would have to start by taking the derivative of this outer layer function, which according to my derivative rules up here, so a to a power, the derivative of that again would be a to the power times the natural log of the base a. So here the base a is 2, so I would start by having 2 to the power as the derivative times the natural log of the base of 2. The power is still 3x because I keep my inner function intact when I'm doing the derivative of the outer layer, but then I will need to multiply the outside of this derivative by the derivative of 3x, which is 3. And I can multiply the 3 with ln 2 because they're both constants, but I cannot multiply this 3 with this 2 because this is not a factor of 2. It's not like 2 times 3x. I mean, technically there is a factor of 2 there, but the 3x is telling me how many factors of 2 there are. And since x is varying, then the number of factors of 2 are also varying. So I can't take this one and multiply it to the 3. But I can do this. This is typically how we rewrite this. I put my constants in front, so 3 ln of 2, and then I put my exponential function at the end. So this would be my derivative, or my slopes, for this function here. Sometimes I've noticed, like in the AP test questions that are multiple choice, sometimes they take this 3 and they bring it inside to the natural log, and sometimes you might see this written as ln of 8 times 2 to the 3x. Sometimes, but not always. So just remember that's called the power property of logs. Sometimes they use it to simplify their answer or to combine like a coefficient with a log. But again, not always. So just be aware that it's a thing. Okay, so example 4 is another type of derivative of an exponential function that's just a little bit more complicated. So in this example, I'm using an exponential function, so it's like 5 to a power. So the 5 is my base. So the a in this case is 5. So I'll have to multiply by the natural log at 5 when I'm doing natural log of 5 when I'm doing the derivative of the outer layer. So let me just start by writing that out. So my outer layer is 5 to a power. My inner layer is that quadratic function inside, the negative 3x squared plus 7. That function has been plugged into the exponent, so it's the inside of 5 to a power. So when I'm taking the derivative of 5 to a power, according to the rule, the exponential function rule, I would start by just repeating that. So it's 5 to the power, right? I keep my inner function intact. I don't change it at first. And then according to the derivative of an exponent rule, I'd have to then multiply by the natural log of that 5. So this is the derivative of my outer layer. But then I'd have to come around and multiply that by the derivative of the inside. So the derivative of the inside, I have to use the power rule and the sum rule and the constant rule. I would get negative 6x plus 0 technically, since derivative of 7 is 0. So I'd have to multiply the outside of this by negative 6x. And so again, I would write my final answer. I typically I would move all of this stuff to the front. So negative 6, maybe I can think of it as the constants first. So negative 6 times ln of 5, and then times x. So all of that is a constant times x. And then that is all being multiplied to 5 to the power of negative 3x squared plus 7. How you order your like factors of your product really doesn't matter that much. We just usually like to put all the things on base level in front so we don't confuse what's in the exponent of the exponential function. But the order in which you write these here it doesn't really matter. Okay, and so that would be our final derivative for this exponential function here. All right, so the back of your outline is looking at scenarios that might be a little bit more challenging or just unconventional. So I wanted to kind of point out a few of those. In example 5, the reason I wanted to give you a few of these is because it is an option, and a very good option, for some of our derivatives of logs. It makes it easier to use properties of logs first before taking the derivative to make it a much less complicated derivative process. So I just want to remind you over here like what our properties of logs are. We have the product property, and what that says is if you have a log of a product, so maybe like A times B, that is equal to the sum of the individual logs of each factor. So if you're multiplying inside the log, then you're adding the logs. And this is because the log, of course, is an exponent. So when bases were being multiplied together, the exponents were being added. And these are the exponents here. So that's the product property. And then we also have the quotient property, which says, okay, so inside your log, suppose you have like two things that were dividing. Well, the division must have happened, or the division that was happening here, the way we handle that with the exponents is by subtracting them. The logs are the exponents. So the log of a quotient is the same thing as subtracting the two separate logs of each of the factors, or of the numerator and denominator. And then I mentioned this one a moment ago. We have the power property, which says if you have, like inside your log, if you have a base to some kind of power, so P would be our power, that's equivalent to having that power become the coefficient of the log. And this is because when you're working with exponents and you have like a power to a power, you multiply the powers. And so the log of A is an exponent and it's being multiplied to whatever A was being raised to. And so these are the three properties that we can sort of keep in mind, and we can use them either way. We can either take a sum of logs and put it into a product, or we could take the product and turn it into a sum, whatever is more advantageous at the moment. But let me show you kind of how we would use these in the context of finding the derivatives. So for this one here, I will have to use the chain rule, but the chain rule will be significantly less complicated if I recognize that inside of my log, what I technically have is an exponent of 1/2. So yes, it's a square root, but a square root is also understood as an exponent of 1/2. And so what I could do is I could use the power property here to rewrite this function and say, okay, I'm going to take this exponent of 1/2 and turn it into the coefficient of my log. So this function, so ln of the square root of x plus 1 is identical to, equivalent to the number 1/2 times the natural log of just x plus 1. So I can turn this more complicated inner function into a very simple linear function, and then I can just have a constant multiple and use the constant multiple rule when I'm taking the derivatives. It's just so much easier. So then the derivative of this function would be the same thing as the derivative of this function. And I still will need to use the chain rule in the sense that I have to plug all of that into my derivative. So it's 1/2 times x plus 1. The 2 is there just because I have to keep the constant from my function as part of my derivative. That's the constant multiple rule. And then the 1/x plus 1 comes from the formula for the derivative of the natural log is 1 over whatever's inside. And then I would need to multiply by the derivative of what's inside, which is just 1. So some would argue that you don't even need the chain rule anymore. Once the derivative of your inner function's 1, you don't need the chain rule. But I just wanted to point out that I am using the chain rule, and it's still giving me the same answer. So my final answer for this would literally just be, you can either write it as 1 over 2x plus 2, or you could keep the 2 factored out either way. But I'll box this answer. Much simpler process than it would have been had I needed to take the derivative of the square root function. So just really helpful to keep these properties in mind and use them before deriving to make your deriving process simpler. Okay, so then in this problem here, I can see that I have a log of base 3. I also notice that inside my log, I have a quotient, which would require me to use the quotient rule combined with the chain rule if I didn't have these properties of logs. But because I do have them, I'm going to use them to make my life easier. So I'm going to rewrite the log base 3 of rad x divided by x plus 5. We're going to think of that as log base 3 of rad x minus the log base 3 of x plus 5. So then when I'm deriving, I could use a difference rule instead of a quotient rule, which, as you remember, is much simpler. Additionally, I notice I have a square root right here that I could use the power property to help me with that. I could rethink of this square root as a 1/2 power. So I'm reimagining it as a fractional exponent. And then I can use this power property to make that a coefficient. So now what I've been able to do is change this chain rule / quotient rule problem into a chain rule / constant multiple and difference rule, which is much, much simpler. So now the derivative of this will equal the following. So for this first part, I just use the constant multiple rule, which says to bring the constant from the original function to the derivative. Then I use the derivative formula for a log base 3. So here my base is 3. So that's my a from my log formula. So this would be 1 over x. That's what the derivative says to do. 1 divided by the inside. And then you multiply that by the constant, which is the natural log of whatever your base is, which is 3. So this is the derivative of the first part. And then I use the difference rule to just find the derivative of the second part and subtract the two derivatives. So this is also a log of base 3. So I'm going to use the a value of 3 here. And the derivative formula says to divide by whatever's inside the log. So it's 1 over x plus 5, and then you multiply that by the natural log of 3. And I could get a common denominator. I think maybe I will. Let's get a common denominator to combine these together. They already have the ln of 3 in common, so I don't need to worry about that. But this side has a 2x and this side has x plus 5. So I'm going to multiply this one by 2x over 2x. And then I'll multiply this one by x plus 5 over x plus 5. I'm going to do some simplifying work. Actually, maybe I'll erase these properties. Hope you don't mind. And simplify over here. Okay, so now, I'm going to bring this up here. So now I have x plus 5 on the numerator here minus 2x from the second numerator all over my common denominator, which includes a 2x, it includes an x plus 5, and it includes an ln of 3. So these are all the things in my denominator, and now my numerator, I just have x plus 5 minus 2x, which would just become 5 minus x. And again, the order in which you have the factors in the denominator doesn't matter. And then this would be our derivative of this original log function, which I want to point out here that if you had used the chain rule with the quotient rule, you would have eventually ended up with an equivalent expression to this, but it just might have been a lot more of a complicated process to get there than it was using these properties. So just something to think about when you're working through the practice. So in the challenging example type 2, this is back to just chain rule. We're just using chain rule here and not thinking so much about logs or exponents. But it's a chain rule that would end up having some complicated simplifying at the end. So I wanted to just walk through one of these just so you have an idea of how to work out the simplifying at the end. I think pretty much you guys could calculate the derivative because I would need to use the chain rule combined with the quotient rule here. since I do have a quotient as my whole function. So if I'm going to start with the quotient rule, and I'm going to understand that my numerator, which I like to refer to as u, is x. So the derivative of that would just be 1. And then my denominator is v. And I'm going to first think of that as a power of 1/3 because it helps me take the derivative. I can use the power rule. So the derivative of that, this is where we would need the chain rule. It's taking the derivative of the denominator. So I would start with the outer layer, which is the power of 1/3. That's my outer layer. So I would start by doing 1/3 times, and I would leave my inner layer completely intact. I don't take its derivative until after applying the derivative of the outer layer, which says to take the power, bring it in front, and then subtract 1 from the power, leaving me with a negative exponent. Then after all of that's done, then I multiply by the derivative of whatever was inside, and then maybe simplify a little bit. Like I can multiply the 2 and the 1/3 together, so I get 2/3. And then there's this x, which I like to put in front, just because I think it's easier to remember it's there when it's in the front. And then I have the x squared plus 4 to the negative 2/3. So this is my derivative of the denominator. So I'm going to start over here with quotient rule by doing u prime v minus v prime u over v squared. So that would look something like this. So 1 times my denominator, and I'll write my denominator as a power of 1/3. And then minus v prime, which was all of that stuff we just found, x squared plus 4 to the negative 2/3, and then times u, which was x. So that's my numerator, and it's all over my denominator squared. So I'll think of that as x squared plus 4 to the 1/3, and then all of that as being squared. So first I'll simplify a little bit, and then I'll simplify a lot. So the simplifying a little bit would be like using the power property of exponents here to multiply those powers together. And then I'll combine these x's as well, and I will add their powers together. So when you're multiplying same bases, you add the powers. So now I have this. Actually, while I'm doing that, so while I'm simplifying a little, I will also make the denominator of my numerator more obvious. Because see how I have a 3? That's going to be in the denominator. And then this part, since it has a negative exponent, will also be in the denominator. So I will have 2 in the numerator of the numerator, and then x times x, which is x squared. Those are both in the numerator. But then in the denominator, I'll have the 3, and then I'll have the x squared plus 4 to the 2/3. And that is all just my numerator, and then that is all being divided by x squared plus 4 again to the 2/3. So this is my derivative, but as you can see, it needs some simplifying. Leaving it like this would not be wise, especially if you're using it for something else. So what I'm going to do is get a common denominator in the numerator. I already have the 3 and the x squared plus 4 to the 2/3 in this denominator. I just need to multiply it also to the other denominator. And then whatever you multiply to the denominator, you also then need to multiply to the numerator. So then what that ends up creating is I have this 3, and then I have this common factor, x squared plus 4, or common base, I should say, along with this common base. These are the same base, and they're being raised to 2 different powers. So what I could do is add their powers together. That's using a rule of exponents that says if you're multiplying same bases, x squared plus 4, x squared plus 4, they're raised to different powers, you add the powers. So this 3 right here is getting multiplied to x squared plus 4 to the 3/3 power, 2/3 plus 1/3. And then I'm subtracting from that my 2x squared. All of that is over my common denominator of 3 times x squared plus 4 to the 2/3. All of that is over the original denominator of x squared plus 4 to the 2/3. So now what we need to recognize is that I don't need to think of this as being in parentheses because 3 over 3, that just equals 1. So I don't really need that. I can distribute my 3x squared, or my 3, excuse me, to the x squared plus 4. And then I could combine like terms with the 3 and the 2. What I can also recognize is that when you're dividing a fraction by this quantity, that's really the same thing as multiplying this fraction from the numerator by the reciprocal of the denominator. So I'm really multiplying by 1 over x squared plus 4 to the 2/3. Okay, and then again, I'm multiplying same base, x squared plus 4, with another same base. So I can then add these exponents. So when all is said and done with this question, I would end up with, maybe I'll show that part. So I'd have 3x squared plus 12 minus 2x squared all over, and then I could multiply this to that, so 3 times x squared plus 4 now to the 4/3 that I get from adding powers. That's how you multiply those together. When you have same base to one power, same base to another power, you add the powers. So the 2/3 plus 2/3 became 4/3. And then in the numerator, I can combine my like terms of 3x squared and negative 2x squared. And so I end up with positive x squared plus 12 in the numerator, all over 3 times the quantity x squared plus 4 raised to the power of 4/3. Now this is a much cleaner, tighter, appropriate looking derivative for this original function here. This could help us find the slopes of the tangent lines to this curve. It could help us find instantaneous rates of change. We could find where the tangent lines are horizontal. It'd be much easier when your derivative is simplified and wrapped up nicely like this one. So I just kind of wanted to go through that process, remind you of rules of exponents because they come in really handy when we're dealing with radicals, and also remind you that simplifying or finding a common denominator in the numerator can make things turn out much nicer than if I were to just leave it like this. Okay, so our last example is when we have to use the chain rule more than just one time. So the chain rule can be used repeatedly. Like you can just keep pulling layer after layer after layer and just keep multiplying by derivatives of the inside. So I could have 3-layer, 4-layer, 5-layer problems. The ones I have here are only 3-layer, and I think that's pretty much the furthest it would go, like on the AP test also. But just so you know, you can use the chain rule an infinite number of times. So in this case, what I want you to notice is that you have cosine is one of the functions. The inside of it is a second function. And then all of that is being squared. So I technically have 3 layers of function. So it's like those like Russian dolls, you know, where you open up one and then there's like another one inside. And then you open that one and then there's another one inside, and so on and so forth. So the 8 theta was plugged into cosine, and then all of that was plugged into a squaring function. So this technically is a function composed with 2 other functions. It's like an f of g of h type of situation. So when I use the chain rule, you just start from the outer layer and work your way in. That's the order of derivative taking. So in this case, my most outside layer was this one. The power was the one that was most on the outside. So I don't know how else to say that other than to just say it was the most outside. And then the middle layer is the cosine. This is like the middle child. So don't ignore it, right? Middle childs get cranky when you ignore them. And then we have our inmost layer. Now let's see, what color should I use for that? Light blue. So that was our most inside, or the baby of the family. Okay, so we're going to start by taking the derivative of the most outside layer, which was a power rule. So I start by multiplying the power in front and subtracting 1 from the power. keeping all of this inside stuff intact. So cosine of 8 theta is still cosine 8 theta. Then I work my way to the middle layer and I take the derivative of the cosine function, which is negative sine. Meanwhile, the 8 theta is still intact. Oh, and by the way, don't get thrown off by the theta. Theta is just a variable. It represents a variable angle. And we can treat it just like we would treat the letter x or t or something like that. Sorry, okay, so here I have negative sine of 8 theta. Then I get all the way to that inside piece. And then I have to multiply that by the derivative of 8 theta. So think of this as like 8x. It's like a linear function. And the slope would just be 8. So the derivative is just 8. So this was the derivative of my outer layer. The derivative of the most outside. And then and by the way, whenever you take a new derivative, you connect them with multiplication. So then I multiply that by the derivative of the middle layer. And then I connected that with multiplication to the derivative of the most inside. It's just one long string of multiplication, and it's just outer derivative times middle derivative times inner derivative. And then we do some simplifying at the end. I'll do this down here. So I'll multiply my constants together. So I have 2 times negative 1 times 8. And then I'll put my sine and cosine functions together. And so this would be my derivative of cosine squared of 8 theta. So this would give me my slopes of my tangent lines to this function and any other type of instantaneous rate of change information that I needed to find. This would be the derivative for that, my h prime of theta. Okay, and then in example B here, we have another similar type of triple chain is what I like to call these. We've got a triple layer function. So we have to kind of figure out what's the most outside, what's the middle, and what's the inside. So the most outside, the outer layer, would be e to a power, because that's the thing that's like most outside. Then if you look inside the function, you now have this middle layer of sine of something. And then if you go inside of that, the most inside, you have your cubic function, your x cubed minus 2. So according to the chain rule, you always begin by deriving the outside. So I am going to start by taking the derivative of my most outside layer, which is e to a power. That's like the easiest derivative ever anyway, so I like starting with that one. So it's e to the power. Okay, check. Did the outer layer. But remember, when you're doing that, you want to keep all of the other parts intact. You leave the sign of x cubed minus 2 as sine of x cubed minus 2. You don't mess with that until you get down to outside of the derivative. And then you connect the derivative of sine to this derivative through multiplication. So derivative of sine would be cosine. But while you're taking the derivative of sine, you're leaving the x cubed minus 2 completely intact. It's not until after you finish your derivative of cosine and then outside of that is where you'd multiply by the derivative of the most inside, which is 3x squared. And again, you connect all your derivatives with multiplication and then you look to see what you can simplify at the end. And honestly, I can't really simplify any of this, although I will write it in a way that I prefer. I typically like to put like my x terms in the front. Not that it matters. So this is just me. You don't need to do this. And then I like to put all things that are on base level in front of the exponential function so that I don't confuse it with what's inside the exponent. So I always put like my exponential functions at the end. So at the very end, I have e to the power of sine of x cubed minus 2. And you'll notice whenever you're doing a derivative of an exponential function, like this same expression will appear in its own derivative. That's just how it works. And then here are the derivatives of all the other parts as well. So this final answer here, all of that together, would be the derivative of this original exponential function. And I think I've covered most of the scenarios you're going to come across in the practice and in this class. Of course, there may be slight variations of these that I hope you can sort of think through. But as always, circle anything you have questions on and let me know, and I'll be sure to go through them thoroughly in class when I see you Friday. Hope you had a fun Halloween, and I'll see you soon. Bye.